As we've been following the rules for drawing Lewis structures, I've been leaving out one of the rules that refers to formal charges. So let's take care of that right now. I'm going to draw the Lewis structure of sodium hydroxide. And as always, I'm going to follow the steps that we had before. Now, maybe you're ready to not look at them this time. That would be great. If not, remember you're working towards that. So let me walk through the steps here. First of all, what I see for the first time in this chapter is that I'm looking at the formula of an ionic compound, a metal and a non-metal. So really, I want to draw the Lewis structures of a sodium ion and a hydroxide ion. And don't you dare connect the sodium to the oxygen with a line. That represents a covalent bond, shared electrons. No way, this is ionic. So let's see about the sodium ion. That's going to be easy. A neutral sodium atom has one valence electron. But if I made sodium plus, I took that valence electron away, I'm going to leave it just like that with no valence electrons. Of course, I know that the next level down will be full, but I think I'll just leave the sodium like that and focus on the hydroxide ion. So how many valence electrons can I add up? 6 for the oxygen. The hydrogen has 1. And now we're going to use another part of Rule 1 we didn't use before. It said that if we had an ion, we were going to add or subtract the number of electrons indicated by the charge. Now, this is a negatively charged ion, and we're counting electrons, so that gives me 1 more electron for a total of 8. All right, now put the skeleton together with single bonds. That took 2 electrons. Now fill up the octets till I get up, starting with the terminal atoms. 2, 4, 6, 8. And I ran out of electrons just as I completed the octet on the oxygen. The hydrogen's happy with its 2 electrons. I'm done. And I have no extra electrons. I don't have any insufficient octets, nothing like that. All I have to do is double check the structure. Total number of electrons is 8. 2, 4, 6, 8. And the oxygen is happy. 2, 4, 6, 8. And the hydrogen has 2. Did you ever wonder why a hydroxide ion had a negative charge? Because it needs an extra electron to end up having a stable structure, obeying the octet rule. So if I was putting the sodium back, I would just write the sodium ion near it. But again, don't you dare draw the line. Now, I'm showing that the hydroxide ion has a negative charge on it somewhere. But it's helpful sometimes to look at which atom of the polyatomic ion actually has the charge. That's what we call the formal charge. That's the charge assigned to individual atoms. And often in textbooks or on websites, you'll see a formula, a mathematical formula to calculate that. That breaks my heart because you really don't need a formula. And if you think you do, you're going to give up when you forget it. The formal charge is just the difference between the number of electrons you expect it to have from its position in the periodic table versus the number of electrons it's actually contributing to the structure. In other words, how many electrons should it have versus how many does it have? So if I look at that hydroxide ion again, first let's look at the oxygen. From its position in the periodic table, I expect it to have 6 valence electrons. But in this structure, how many is it actually contributing? Now for formal charge, I'm going to do a different kind of count than I did for the octet rule. When I looked at the octet rule, I counted the total number of electrons around the oxygen, and that was a happy octet. But when I'm counting for the formal charge, I'm asking how many of those electrons came from the oxygen. And when I do that, I'm treating the bond as if one electron came from the oxygen and one came from the hydrogen. So let's see how many electrons that oxygen is contributing. The lone pairs, 2, 4, 6, and 1 for the bond, that's 7 electrons. I expected oxygen to have 6 valence electrons. It's contributing 7 valence electrons. It's got 1 extra electron, 1 extra negative. It has a negative formal charge. And I just circle my formal charges to make them a little bit more visible. All right, let's try it for the hydrogen. How many valence electrons do I expect hydrogen to have? From its position in the periodic table, I expect it to have 1. How many is it contributing to this structure? 1 from the bond. So the hydrogen has no formal charge. The beautiful thing about this is that the sum of the formal charges has to add up to the overall charge. So we've got a -1 for the oxygen, 0 formal charge for the hydrogen. That adds up to -1 overall, which is what we saw for the overall hydroxide ion. Pretty good, huh? So an even more detailed structure of sodium hydroxide would be to show those 2 ions with their formal charges. And that's what I'm going to do from now on. Perhaps we should practice more of that. All right, the top one on that slide. And I hope you know what that's called. That is ammonium bromide. And the first thing we have to recognize is that that is an ionic compound. Even though there's no metal in it, ammonium is the only positive ion on the list of ions that you memorize. I'm so sorry. So that's really an ammonium ion and a bromide ion. Now, you saw me do the sodium hydroxide. It would be great if you could pause the video and do this yourself. All right, here I go. For the ammonium, nitrogen has 5 valence electrons. Each hydrogen has 1, but there's 4 of them. And this time the charge is positive. We've taken an electron away. I'm going to subtract an electron. So that leaves me with 8 valence electrons for ammonium. Step 2, put the skeleton together with single bonds. First atom is the central atom. Now, what did we just accomplish? I used up all 8 electrons in making the skeleton. So I don't have to fix any incomplete octets. I used up all 8. I don't have any extra electrons to position. So now I'm ready to look at step 6. Rule 6 says, if there are formal charges of opposite sign on adjacent atoms. Okay, so we better put some formal charges on this. From now on, when do I worry about formal charge? I always worry about formal charge. And I know there better be formal charge in there because it's an ion. The formal charges on the individual atoms have to add up to +1. So, again, good place to pause the video and make sure you can assign the formal charges to the ammonium ion. I see a nitrogen in the center. I expect it to have 5 valence electrons from its position in the periodic table. But when I'm counting for formal charge, I'm asking how many of those electrons came from the nitrogen. And remember, we're treating each bond as if each atom contributed 1 electron to it. So although there's a total of 2, 4, 6, 8 electrons around the nitrogen, only 1, 2, 3, 4 of them came from the nitrogen. I expect nitrogen to have 5 valence electrons. It's contributing 4. It's missing an electron. It's missing a negative, so it's positive. And again, I'm going to circle the formal charge to make it more visible. What about the hydrogens? I expect 1 valence electron. It's contributing 1 valence electron. No formal charge on the hydrogens. And a double check, the formal charges on the ammonium add up to +1, which it should have. Right on. Now, NH3 is ammonia. NH4 is the positively charged ammonium ion. Why? Because when you stick 4 hydrogens on a nitrogen, it ends up with a positive formal charge. No more memorizing. It all makes sense now. All right, what about the bromide ion? Bromine had 7 valence electrons, but it's got a -1 charge, so we're going to add 1 for 8 electrons. 2, 4, 6, 8, complete octet for the bromine. And when do we worry about formal charge? We always worry about formal charge. From its position in the periodic table, I expect bromine to have 7 valence electrons, but it's contributing 8. It's got an extra electron. It's got a negative charge of a single negative charge on it. So there is the Lewis structure of ammonium bromide. And don't you dare draw a covalent bond, a line connecting the ammonium and the bromide. It's not covalent. It's ionic. All right, let's try the next one. And I hope you know what that's called. That's calcium sulfite, right? And another ionic compound. I see a metal and nonmetal. That is really calcium 2+ and sulfite 2-. Now the calcium 2+ ion, I'm going to treat like the sodium ion on the previous slide. Neutral calcium has 2 valence electrons, but when I made it 2+, there's no electrons left. So let's focus on the sulfite ion. Sulfur has 6 valence electrons. Oxygen has 6, and there's 3 of them. There's a net charge of -2, so we're going to have to add 2 more electrons. 26 electrons. On to the next step. The skeleton, connected with single bonds. The sulfur is the first atom, so it goes in the center. Now, on to step 3. Starting with the terminal atoms, we're going to complete the octets on the atoms. We've got 6 electrons already. 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. And it came out exactly right. I've completed the octets on all the atoms with 26 electrons. No electrons missing, no extra electrons. So that takes care of steps 4 and 5 as well. Now, step number 6 deals with the formal charge. When do I worry about formal charge? I always worry about formal charge. I want you to assign formal charges to those atoms. Go ahead and pause the video. I see that each oxygen has a negative charge, and the sulfur has a positive charge. I expect sulfur to have 6 valence electrons from its position in the periodic table, but here it's contributing only 5. 2 in the lone pair belong completely to the sulfur, and then 1 for each of the bonds. So the good thing is when I add up the formal charges on the atoms in the sulfite ion, it adds up to -2 overall. Woohoo! But wait, there's more. Rule number 6 says, when I have formal charge of opposite signs on adjacent atoms, get rid of it by putting a lone pair from a negatively charged atom into a double bond between the 2 atoms. Take a lone pair from a negatively charged atom and put it into a double bond between the 2 atoms. Do this only if the positively charged atom is allowed to exceed the octet. Well, let's check. Sulfur is in the 3rd period, so it can use its d orbitals. Yes, sulfur can exceed the octet. So now I'm ready for my final structure. I've now got a double bond there because I moved an electron pair. Nothing else changed. Now let's double check the formal charges. That oxygen with the double bond, if you look, now is contributing 2, 4, 5, 6 electrons, just like I expect, no formal charge anymore. And the sulfur is contributing 2, 3, 4, 5, 6, no formal charge on the sulfur. So we've minimized the formal charge by making a double bond. Pretty cool, huh? So if I wanted to, let's just make a note there, that minimizes the formal charge. Now, if I wanted to put the calcium 2 plus with it, I would write it near it. But don't you dare draw a line connecting them. They're ionic. It's not covalent. Now, I can show you something else cool while we've got that. I haven't shown you how to write the formula of Oxy Acids yet. If I add 2 H pluses to a sulfite ion, I get sulfurous acid. The skeleton is not what you think from looking at the formula. The hydrogen is not attached to the sulfur. The hydrogen's written at the beginning of the name just to say, woohoo, hydrogen, it's an acid. What I do to write the structure is I look at the sulfite ion and I'm going to add H pluses to it. And all of chemistry is opposite charge goes together. If you were an H plus, you would want to stick to an O minus. Right on. So, the Lewis structure of sulfurous acid sticks the hydrogens on like that. And you can double check that structure, right? Total number of electrons. Every atom has a happy octet, or if not, I know why. Sulfur exceeds the octet, but we decided that that was okay because it was in the third period. So far, so good. But wait, there's more. I pulled a fast one when I made the double bond in that sulfite ion. I made a double bond to the oxygen on the top. But what was special about that oxygen? We need to look in a little more detail, and I'm going to use that sulfite ion as an example. I'll explain the tidal resonance as we go. So I'm going to quickly redraw the first structure we had for the sulfite ion that had the formal charges on all the atoms. Now, I saw adjacent opposite formal charge, and when I see that, rule number 6 for Lewis structure says make a double bond. But what was so special about the oxygen on the top? Nothing. I could make a double bond to the oxygen on the top, and I'm just redrawing our final structure from the previous slide. Or I could have made a double bond to the oxygen on the left-hand side. Or I could have made a double bond to the oxygen on the right-hand side. Whoops, I meant a lone pair there. Now, what I've drawn there may look the same, but we call them resonance structures or resonance contributors. And we relate them by drawing double-headed resonance arrows. Now, I want to point out that those are very, very different from equilibrium arrows. Equilibrium arrows had 2 separate arrows. That's not this. It's important that resonance structures have 2 heads on the same arrow because of what it means. It does not mean a chemical change is happening. It does not mean the electrons are moving. It does not mean the bonds are moving. What it means is that the true blended structure of sulfite ion looks a little bit like structure number 1, looks a little bit like structure number 2, and looks a little bit like structure number 3. In other words, the bond to the top oxygen isn't a double bond and it isn't a single bond, it's a blend. An analogy I can make is if I tell you I've got a new puppy that's half German Shepherd and half Chihuahua. Can you imagine my puppy? It's not that it's a German Shepherd 1 second and a Chihuahua the next second. It's always the same puppy. I'm just telling you it looks a little bit like one and a little bit like the other because there's no single name for what it really is. So the same thing with this sulfite ion. There is only one sulfite ion. Nothing's moving, nothing's changing, but I'm saying it looks a little bit like each one of those structures. So just like you blended your image of a German Shepherd and a Chihuahua in your head to see my puppy, I'm going to blend those structures to make a hybrid of all those resonance structures. In other words, the true sulfite ion has not a double bond to each one of those oxygens, not a single bond, but somewhere in between. So I'm going to draw this dashed line as a partial bond. It's somewhere between a bond and a double bond in the true sulfite ion. So I think this, but I draw the resonance structures on the other side. Think of as this structure. Now, I could figure out what fraction of a bond is between them. What I saw on the previous slide is that I was spreading 4 sulfur oxygen bonds over 3 positions. 4 sulfur oxygen bond over 3 positions. So that's 4/3 of a bond between the sulfur and each oxygen, or equivalently a bond and a third between the sulfur and each oxygen. That's called the bond order. We've had single bonds, the bond order there is 1. Double bond, the bond order is 2. Triple bond, the bond order is 3. But you might be surprised that I can have a fractional bond order. The problem is that the electrons in truth are really spread over the whole molecule. They're not stuck between a pair of atoms. We do what we can do. We draw resonance structures, but we think of them like this. Now, let's see. I could also think about what charge is on each one of those oxygens in the true single structure. The overall charge is -2, and it's spread over the oxygens in the resonance contributors. So I'm going to spread -2 over 3 oxygens. I think the charge on each one of those oxygens is -2/3. And that adds up overall to I hope -2. Let me see, -4, let me see. Yep, -2. Good. So we think of the resonance hybrid, but we draw the resonance structures. And remember, in resonance forms, there's one single structure. The electrons are not moving around, just like my puppy's not a German Shepherd 1 second and a Chihuahua the next one. Let's practice a couple of examples. The first example is O3, and I don't care if you know that that is the ozone molecule. I just care that we can draw the Lewis structure for it. So I'm going to follow through those same steps for drawing Lewis structures. First, I'm going to add up the number of valence electrons. Each oxygen has 6 valence electrons, and there's 3 oxygens. So we're going to position 18. Now I'm going to put the skeleton together. And as I say, that's probably the hardest part. They're going to be in a straight line. You might wonder why they don't make a ring, make a triangle. Take my word for it, they don't. That ring would be too small to do that. Those atoms don't want to be that close together. Okay, so now I've positioned 4 electrons already. Now I'm going to start with the terminal atoms to complete the octets at 4, 6, 8, 10, 12, 14, 16. And I've done the terminal atoms. There's 18. Now I've run out of electrons before I completed the octet on the central oxygen. And rule number 4 says if I don't have enough electrons to satisfy the octets of all atoms, put an electron pair from an adjacent atom into a double bond. Okay, but which adjacent atom? When you have a choice, that is your cue that you should draw resonance forms. In one resonance form, I'm going to show a double bond between these oxygens and leave everything else the same. But there's a resonance contributor. Note the double-headed error there. There's another resonance structure where I made the double bond between the central oxygen and the oxygen on the right. Which one's the right one? They both are. Really, the 2-ozone molecule is a blend of those two. Now, wait a minute. I'm not done. When do I worry about formal charge? I always worry about formal charge. But you say, wait, this is a neutral molecule overall. That doesn't mean that individual atoms don't have charge. That doesn't mean that there are no formal charge. So from now on, we check every single atom. All right. The oxygen on the far left, in the left-hand structure, is contributing 2, 4, 5, 6. I expect 6. No formal charge. The central oxygen, 2, 3, 4, 5 are contributed. I expected 6. It's missing an electron. It's positive. The oxygen on the right, 2, 4, 6, and 1 for the bond is 7. I expected 6. There's an extra electron. That's negative. The total charge adds up to neutral overall. Good. Now that's a big mess there. That should look like that. Okay. Now, one of the rules says when I have adjacent opposite formal charge, I should try to make a double bond to minimize the formal charge, but I can't do that this time. Oxygen's in the second period. Its valence orbitals are the 2s and the 3,2p. There are no nearby d orbitals. You cannot exceed the octet for a second row element. That's the best we can do. So, similarly, the formal charge is here, like that. Double check the structure, that the total number of electrons is correct. 2, 4, 6, 8, 10, 12, 14, 16, 18, good. And that each atom has a happy octet. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. And I'm reminded one more time that there are 2 different counts. When I count for the happy octet, I'm looking at the total number of electrons around the atom. When I'm counting for the formal charge, I'm counting how many of those electrons came from that atom. So those are the resonance contributors. If I imagine the resonance hybrid, the true ozone molecule doesn't have a double bond on one side and a single bond on the other. What's the bond order in the true form? I'm spreading 3 bonds over 2 positions. Each one of those bonds is really a bond and a half. And I'm trying to get in the habit of not showing you the hybrid, but I will this time. Whoops, we think the hybrid. We're not going to draw it anymore after this. Bond and a half, bond and a half. Positive charge, negative a half, negative 1/2. How's that grab you? All right, one last example for resonance. OCN. And I have to tell you that the skeleton is this. The first atom is not the central atom this time. And how do you know that? Because I'm telling you that. And I will always tell you that. Even under a pressure situation. Nudge, nudge. Wink, wink. But with that information, I hope you can draw the Lewis structure for that ion. Go ahead. Pause the video. Here I go. Oxygen has 6 valence electrons. Carbon has 4. Nitrogen has 5. We've got a charge of -1, so we've got to add in an extra electron. 16 electrons. Here I go. Terminal atoms first. We've got 4 electrons already. 6, 8, 10, 12, 14, 16. And I ran out of electrons before I completed the octet on the carbon. So rule number 4 says I have to make some multiple bonds. Now that carbon needs 2 more pairs. Where are they going to come from? I have a choice. This is my cue to draw resonance forms. I could give both bonds from the oxygen, which would leave me with a structure like that. Or I could make one double bond to the oxygen and one double bond to the nitrogen. Or I could make both double bonds to the nitrogen. When I have a choice, I should show the choices. I should show multiple resonance structures, multiple resonance contributors. Now, I don't want to belabor the point. Those are good structures, but what they don't have yet are their formal charges. And I don't want to bore you with that. I'll just slap them down. We can discuss that at our Zoom meeting if you want. You will see that there are no adjacent opposite formal charges. And you'll also see that the total formal charge adds up to -1 like it always should. Okay, I want to blend those structures to get a picture of the true ion. With resonance forms, I'm saying it looks a little bit like one, a little bit like the other, and a little bit like the third one. But in this case, I don't have equivalent resonance contributors like I had before. So when I blend them in together, I'm not going to weigh the contributions equally. Some resonance forms are more stable than others. And what I will say first is that this one with separation of charge is very, very minor. It wouldn't contribute much to my overall structure. I see separation of charge. I see 2 different atoms with charges on it. To compare that to my puppy analogy, that would be like saying my dog was mostly German Shepherd, but there was a Chihuahua 8 generations ago. I wouldn't really have to worry about the Chihuahua. Similarly, I'm not going to blend this resonance structure into my hybrid significantly. The other 2 structures have equal charge separation, a single negative charge on an atom. But one of those is more important than the others. And what we will see is that the major one has the negative charge on the more electronegative atom. Oxygen is more electronegative than nitrogen. And you remember why. As we go across the periodic table, carbon, nitrogen, and oxygen, as we go across, the important structural feature is the increasing positive charge on the nucleus. The more positive charge on the oxygen nucleus means it can handle the negative charge better. So when I blend those structures together, I would say that the true ion looks most like the structure I labeled major. In other words, although the carbon-nitrogen bond is somewhere between triple and double, it's closer to a triple bond than a double bond. And I can't draw you a reasonable hybrid for this because I don't know how much weighting to give each structure. Fun, huh? We'll get a lot of chance to practice that in our practice problems and on our assignment and in our Zoom meeting.